Assalamualaikum, selamat sejahtera, selamat tengah hari. Apa khabar semua?
Waalaikumsalam, sehat.
Okay, today we have additional members of the class from 243 ya. Betul kan?
Betul, sir.
Right. So you're welcome to be in the class. Today kita akan continue dengan vapor cycle, which is the last chapter. I'm not sure lah yang 243 bila last class you dengan Dr. Zaki, because he was down with COVID last 2 weeks saya rasa. But anyway, you can apa tu? Take notes lah apa yang saya nak bagi lecture hari ni. Right, let's not waste our time. In the meantime, kelas saya, please register your attendance ya. Okay, can you see the screen? I think first of all, I would like to explain a little bit about assignment 2. So for everyone's information, I have assigned the assignment 2 in the Google Classroom. So you can check the assignment later on. The assignment is a group work. Let's see whether I can open up. Okay, so this assignment is 20% of your total final marks. So please make sure you do properly. Spend enough time to do this to get it right. Okay, so for this assignment, there will be 2 questions. Now the first part is basically the format that we need to follow because the engineering courses now we need to have complex engineering problems. Yeah, so here if you can see the complex engineering problem right in the middle here. So the WP1 is for knowledge, WP2 is for conflicting requirements, and P3 for analysis. So basically these are the components of complex engineering that we wanted to test. So these elements are in the question itself. Okay, right, so if you check the assignment later on, there's a learning outcomes for this. Basically we wanted to cover the first and second law thermodynamics analysis, and then we wanted to evaluate the thermodynamic system performance. So this is mostly the chapters after semester break the other day. Okay, right, there are 2 questions. The first question is 20 marks. So you need to go through all these questions. And the second question is 40 marks. Yeah? Right. Submission is on the 7th of February. So you have around 2 weeks to get it done. And Due time is 11:59 on the 7th itself. So again, this is a group work. How many of you in the class? For my class, saya lupa dah. 20 berapa? Anyone? Class rep? Okay, tak ada. Right, I will check again. How many in the class? Cumanya for this assignment, maximum is 4 students in a group. Okay. Now, grouping we will discuss in the WhatsApp group later on after class. Okay, so these are all the descriptions of the complex engineering that we wanted to test in the assignment 2. Okay, so please go to the classroom assignment, and then you can download this assignment, have a look. Grouping will be discussed and finalized in the WhatsApp group. Okay, so I think that's for the assignment, and today we'll be discussing about chapter 8, vapor cycles. So I think this is the most interesting part for this course, because here you will see how whatever that you have learned from chapter 1 will be applied. Okay, so at the end of this class, you will be able to explain the basic concepts and apply and correlate the concept with equations, principles to solve engineering problems. So what we have here is engineering problems. We have, I think by now, everyone is aware of Carnot vapor cycles. So through this chapter, we'll be looking at the Carnot cycles and why it is not practical for engineering application. This is followed by principles of Rankine power cycle, because Carnot is not good. So we have a better power cycle, which is known as ideal Rankine power cycle. And using this Rankine power cycle, we'll be looking at pressure and temperature effect, not A, this is E, effect on efficiency. On top of that will be, you should be able to explain the principle of reheat. Now, the Carnot, because of the limitations, we introduce Rankine power cycle. Okay, the ideal Rankine power cycle. But this also has limitations. So as an improvement to ideal Rankine power cycle, so we'll have here reheat Rankine power cycle. Okay, and the others include TS diagram as well as problem solving. So for today, we'll be looking at these 3 major components. Carnot vapor cycle. This is the ideal. This is a reversible power cycle because there is no irreversibilities. So Rankine is the ideal power cycle. And we also have the improved version of Rankine, which is reheat Rankine cycle. Right. The first thing that you need to do is to recall what we have learned before. So I have shared again here the Carnot cycle. There are 4 steps. I hope you are very familiar with these 4 steps now, so that we can skip explanation on this. Let's look at here. So from that 4 cycles, we transform it into PV diagram. And so PV diagram, if you follow the sequence, this is isothermal expansion, followed by adiabatic expansion, and then we have isothermal compression from point 4 to point 1 to the initial point. Initial state is adiabatic compression. So if you follow this process, this is Carnot heat engine, and if you reverse the process, for example, from point 1 to point 2 here, this is adiabatic expansion, and from point 2 to point 3, isothermal expansion. From point 3 to point 4, adiabatic compression, and point 4 to point 1 is isothermal compression. So if you reverse the cycle, you will get a refrigerant cycle. Okay, for the normal cycle, you need heat input to generate work, and for this cycle to work, we have Clausius statement says you need to discharge the heat so that the cycle works. Now for this, you absorb the heat from the sink area, and then for this you need work in so that the system can work, so you discharge the heat to the source area. Okay, so if we have this in mind, then it's much easier because we wanted to relate this PV diagram with the applications. Yeah? Right, from chapter 7, now this is chapter 6, P and V. So P versus V. Oh, okay, saya lupa tadi. The area inside this diamond is the work net out, and the area inside this diamond shape here is work net in. Okay, because PV is work kan. Now, if we go back to chapter 7, the Carnot cycle, and for the cycle, we draw TS diagram, temperature versus entropy. So what we'll get is a nice square here. Yeah. So when we have a nice square, now from point 1 to point 2 is isothermal expansion. Point 1 to point 2 is isothermal expansion. So you have a straight line, nice straight line, and expansion entropy improves or increase. And from point 2 to point 3, we have here adiabatic expansion. So kita tak ada increase because this is adiabatic, this is entropy. So adiabatic process, so delta S is 0, that's why you have a straight line down. But this is expansion, adiabatic. And from point 3 to point 1 is isothermal compression. So you have here straight line because this is isothermal process, and a compression, so you will have change in entropy, and from 0.4 to 0.1 is again adiabatic compression. Okay, that's why you will have a straight line. As a result, we have a nice square shape compared to PV diagram where you have a diamond shape. Okay, right. Now, where do we apply these two concepts for theory and power cycles? A heat engine for power generation, and in the refrigeration system for cooling applications. So thermodynamics is very important because this is something that affects our lives, daily lives. So we cannot live without these two now. Okay. So if we look at the first one, heat engine, I'm going slowly today. So if we look at the heat engine, so we have 4 cycle tadi. The first one is expansion, isothermal expansion. Kalau masih ingat tadi kita ada yang pertama is isothermal expansion, yang kedua adiabatic expansion, yang ketiga isothermal compression, yang keempat adiabatic compression. So boleh tak kita identify the 4 cycle ni dekat mana berlaku dalam diagram kita ni? The first one, isothermal expansion. The volume expand and it happens at constant pressure. Anyone? Tak apalah, 243 pun boleh, 220 pun boleh. Look at here, from 0.1 to 0.2 where you have QH. So which part yang ada QH? Bahasa kelas saya ada je yang jawab kan? Jimmy, apa dia?
Dekat boiler.
Dekat boiler, ya. So we have QH here. So we have isothermal expansion at the boiler. Okay. So 0.1 to 0.2 is at the boiler. And then once you identify this, you just follow the process saja lah. Okay, so 0.2 to 0.3 adiabatic expansion. So 0.2 to 0.3 kita ikut clockwise. So this is 0.3. So this happens in the boiler. Adiabatic expansion occurs in turbine, and then isothermal compression in the condenser, and finally adiabatic compression in the pump. Okay, so this is very important because if you relate that diagram tadi, PV diagram and TS diagram, remember kita ada Carnot cycle ni. TS diagram 4 segi cantik, square. PV diagram diamond shape. So you know that now the cycle can be applied in the power plant. Okay, how about this refrigeration punya system? So we have 4 cycle, same cycle, tetapi the process is reverse. So where do we start first? Let's look at this diagram. So point 1 to point 2 is adiabatic expansion, point 2 to point 3 is isothermal. Ni line ni isothermal ya, yang macam curvy ni is horizontal curve is isothermal, vertical curve ini adalah adiabatic ya. So adiabatic, isothermal. So isothermal expansion ada UCQL. So if we look at this diagram, di mana ada QL?
Evaporator.
Okay, the evaporator. Thank you very much. So we have here point 2 to point 3, and then point 3 to point 4, point 4 to point 1, state 1. Okay. So kalau kita baca the diagram now, this is adiabatic expansion. Betul tak betul? Betul lah, sebab this is a valve and this is expansion valve. 2 to 3 evaporation, ada QL in. From point 3 to point 4 kita ada work in, because this is a compression process. And then point 4 to point 1 balik kepada asal, adalah proses apa yang last kali ni? What is the process yang last kali ni? Point 4 to point 1 ni isothermal compression. Yeah. So this is isothermal compression. Okay. Right. So if we know that, now this is a picture yang mungkin kita dah banyak kali tengok. This is a power plant. Di Malaysia pun banyak ni power plant ini. Here I'm showing you this is coal power plant. So ini apa tu? The fuel source. Because we need the fuel source. So burn the fuel to heat up the boiler so that water can be turned into steam, and steam will be passed to turbine to generate the power, and the spent steam going down to the condenser. Steam is now turned back into liquid, so kita pump liquid, go back to the boiler. So this is a cycle where the working fluid, so remember last time kita cerita tentang working fluid. So in the heat engine power cycle, the working fluid is H2O, which is water. In the refrigeration cycle, this working fluid is R134A. Okay, sebab itu dalam chapter 2, pure substances, we teach you about these two fluid of two substances, how they change with temperature and pressure, and what are the properties that you can determine from this steam table, for example, or from the refrigerant table. Okay, so this is the application yang paling besar dalam hidup kita. And if you look at the schematic diagram, so we have coal here. Normally is a crushed ataupun pulverized coal. Coal lumps kita akan pulverize into powder form. So, and then they is conveyed to the boiler. Dekat sini kita ada boiler. Masuk dalam boiler, tetapi dalam case ini kita ada coal. And then this is plus oxygen. So you burn it, so it generates heat. So you have this hot flue gas. Bakar coal, you dapat flue gas, hot flue gas. The hot flue gas is used to heat up the water. This is the coil. Di dalam ni ada, inside this coil you nampak sini biru sejuk dan dia jadi panas. By the time dia sampai sini dia jadi steam. Okay. So inside the coil is water, kita punya working fluid being heat up by the coal combustion. So flue gas yang panas ini selepas kita dah guna untuk panaskan the coil, kita discharge to stack. Yeah. And this is a simplified version. Ada banyak lagi proses sebelum you boleh release the flue gas. Ada dust collector, ada cyclone, ada scrubbing to remove sulfur, to remove NOx, ada one or two more electrostatic precipitator before you can release the gas ni. Okay, otherwise it will pollute our environment. Okay, so what happened to our working fluid selepas dipanaskan di dalam boiler? Now it turns into steam. So this is high pressure steam. So the high pressure steam is now transferred to the turbine, di mana the blade is being turned by the steam, and this is electromagnetic generator. So you generate electricity, so then transmitted to your home using our national grid system. Okay, what happened to the steam? It is now spent steam. Kerana steam sini high pressure, high temperature. So dia dah buat kerja, dia lose energy. So now what comes out adalah lower temperature, low pressure steam. So what we have here at the bottom, coming out from the turbine, we have a condenser. So this is the condenser di mana cold water is used to condense the steam. Cold water ni ada sistem yang mengalir, steam pass through the cold water. They have their own tube, bukan in the same tube. So this is a different tubing system. Tetapi di dalam steam flow ini ada tube untuk coil ataupun untuk cooling water. So the steam is now condensed, collected at the bottom. So now it becomes a water again, a liquid water, a compressed water or saturated liquid water. And then kita pump balik ke boiler, so the process continues. So it becomes a cycle. Now, if you see here a river, because the whole process requires a lot of cooling water. Okay, for power generation, 24 hours operation, you need a lot of water. So that is why power plant is located near river ataupun berdekatan dengan sea. So if you look at this diagram here, you nampak dekat sini. So ada river kan. So this river is basically to discharge heat to our atmosphere. Okay, ada dua konsep lah ya. So dalam case plant ini dia tak pakai discharge yang macam ini because dia ada cooling tower. Okay, so dalam case plant ini dia menggunakan all this cooling tower. You see this vapor ini, the white vapor ini is basically the heat that you wanted to release to the atmosphere, because our atmosphere ini is a good apa ni, source ke sink ni, sink lah kan. Okay, right, so that is how we generate power and how thermodynamic plays a role at the heart of power generation. Okay, boleh faham ya? Can you relate from chapter 1, 2, 3, dah belajar all those properties of water and refrigerant, and then kita belajar entropy, because all these two here is constant entropy, Kita ada enthalpy because flow inside here dia bawa energy in the form of enthalpy. H equals to U plus PV. So we use all that information so that we can design a power plant system. Okay, so and this is another schematic diagram for a power plant. The main reason saya tunjukkan yang ni because this is related to this system. Okay, so concept dia sama. You have a coal, you boil, you burn it, heat up the water, turn into steam. Steam is now channeled to the turbine to turn the turbine, produce electricity. And what happened to the heat after that? Kita condense again, summer process, we condense. And then the liquid water kita cycle balik. So it's just a cycle. This is your working fluid cycle. But here you have a cooling water cycle. So you need a river because you need a lot of water. The cold water initially is supplied to the cooling coil here. So as it meet the hot steam, it condenses the steam. The cooling water receives heat. So now you see it becomes hotter. So the hot cooling water now is supplied to the cooling tower, whereby you have a spray inside here. Inside the cooling tower, the hot water is sprayed. So the water particles and droplets go down. You see this design at the bottom. Kalau tengok sini, dekat bottom sini ni adalah ruang kosong. Yang hitam ni kat bawah ni dia ruang kosong. So that you will have air draft, yeah. This is kita panggil natural air draft. Okay. Yang sejuk dia naik, dia pick up heat daripada hot water and then discharge ke ATM. Okay, ke atmosphere. So you nampak the cooling water system now. Cold water collected at the bottom of this cooling tower. Ni cooling tower. So we collect the cold water, supply to the condenser, dia pick up heat. The hot water now is supplied to the cooling tower. Dalam cooling tower ni dia spray. So you know the water dia tak akan naik ke atas. The water droplets macam air hujan dia akan turun ke bawah. Okay, so from bottom here ada air flow. The shape macam ni is designed to increase the airflow. So air is naturally sucked and then discharge at the bottom. So because of this interaction, cold air, hot water go down, heat transfer occurs. Cold air accept heat from the hot water and then discharge to the top of the cooling tower. Okay. So that is how a power plant work. Boleh faham clear Boleh jelas ke ada tak faham?
Jelas sir.
Alright. So this is the turbine. I think my class ada tunjuk saya sebelum ni. The typical turbine, and if you look at one guy here, so if he is standing here, so maybe his size is about this. So you can imagine how big is the turbine, and you see how many turbines are there. Maybe one or two as spares so that you don't have blackout whenever they have a problem, so they can always switch to another turbine. Okay, now let's go back to our Carnot cycle. We know that Carnot cycle is a reversible cycle. And because this is a reversible cycle, this cycle is the maximum efficiency, maximum power output that you can get. Yeah. So remember that. And because it is a maximum power cycle, instead of using nilai Q, you can use TH and TL for the calculation. Okay, simple. Now, the Carnot cycle, although it is the most efficient, but it is not suitable for application. Kenapa? So, senang saja. You do not need to hafal all this. Just look at this box. Look at the TS diagram. So you have temperature versus entropy diagram. Tadi kita dah tunjuk TS diagram is a nice shape. And the vapor cycle for Carnot system operates within this envelope. Semua orang aware of this envelope. This is a saturation liquid line. This is a saturated vapor line. Okay. So if we understand this, then we can understand the limitations of the Carnot vapor cycle. So macam mana dia limited? Okay, look at the first one. From point 1 to point 2. Okay. This is at the boiler tadi kan? Yeah, the boiler ni. So point 1 to point 2. Okay. If you look at this diagram, the envelope, the maximum temperature yang dia boleh operates ialah at this point here. This is a critical point. Yeah, this is T critical, which is 374 degree Celsius. So that will be the maximum temperature that the Carnot cycle can operate. So kita dah belajar previous chapter the quality of energy. The higher the temperature, the better the quality. Okay, so that means if you want better quality, you want a better performance, you have to work at higher temperature. But this cycle, which operates between or under this envelope, this Hill envelope here, you boleh pergi sampai 374 sahaja. So that is the first limitation. And our friend masuk tadi. Tak ada. And the second limitation is for the turbine. So dekat sini ya, turbine ni. Okay, the turbine from point 2 to point 3. What happened here ialah the turbine cannot handle a mixture. Turbine kita ni is good for steam saja. Okay, so here if you look at the position ni, this is saturated vapor, but the moment it goes into the turbine, what happened? It goes down. So dia duduk dalam what region is this? Saturated liquid vapor mixture. So between point 2 to point 3, our working fluid, which is the water, adalah liquid vapor mixture. So turbine, ni turbine kita kat sini atas ni. So the turbine ni cannot accept vapor plus water. Okay, the turbine efficiency hanya akan tinggi kalau you supply only vapor ataupun steam. Tapi kalau you follow the Carnot cycle, point 2 to point 3, it happens in this region. This region is under the envelope, which is the saturated liquid vapor mixture region. So you will always have yang masuk dekat sini water campur dengan liquid, water. Vapor campur dengan liquid water. So this impacted the blades in the turbine, blades jadi rosak dan sebagainya. Okay, that is why it is not good to operate the Carnot vapor cycle. Okay, proses 4 ke 1, proses yang sini tak apalah because this is just a condenser. Pumping. Okay, this is a pump here. You look at pump sini. So di sini adalah proses di mana pump. So again you ada liquid vapor mixture. So nak pump is good if you can pump hanya liquid water. Okay, kalau ikut Carnot cycle ini, you are pumping a mixture of vapor and liquid saturated saturated water. So that is the limitation of the Carnot cycle. Ada 3 dekat boiler, dekat turbine and also dekat pump. Okay, now ada saintis kata if that is the case, let us operate macam ni. Let us operate at high temperature. Okay, kita keluarkan daripada envelope ini. So yang masuk dekat boiler ni dengan yang keluar is critical water at temperature and pressure above critical temperature. This is 374 in the middle. So this point here is much higher than 374. Okay, and because kita buat dekat critical temperature, so from point 2 this is superheated steam going down to vapor. So tak ada masalah lah. Okay, so you go down here is vapor, you here is superheated steam, and then from point 3 to point 4 kita buat isothermal compression daripada saturated vapor ke saturated liquid, and then daripada point 4 to point 1 kita buat compression adiabatic dalam pump. Okay, but this problem kat sini ialah kalau kita operate macam ni, of course ni is very high, the QL very high. The point is kalau you nak increase efficiency, your QL must be high, your QH because efficiency sama dengan desired, which is work net out over required, which is QH. So the higher ni, the higher quality, so you will get more work net out. Now if you do this, the problem ialah dekat sini pumping. So here you know that this is a constant pressure line. Okay, if you buat line ni, this is a constant pressure line. So the moment dia lepas kat sini, lepas saja bukit ni, so the pressure is variable. Pressure is no longer a constant pressure process. So dekat point dalam boiler ni pun a problem. Tadi kita buat a constant pressure process di dalam boiler, now it becomes a variable pressure. Kemudian kalau kita nak pump water, this is very high pressure. Pumping to a very high pressure will be difficult and will be very costly. So cadangan ini pun tak boleh pakai ya untuk buat power. Right. So conclusion dia ialah Carnot cycle cannot be approximated in actual devices. It's not realistic model. Therefore kita introduce Rankine power cycle. Itu cerita macam mana Rankine power cycle diperkenalkan. Okay, the same thing. So we can go quickly sebab kita dah faham dia punya konsep. We still have boiler, turbine, condenser and pump. remember we are still talking about heat engines. Dia belum masuk lagi refrigeration. Now, if we go back to TS diagram, kalau tadi TS diagram kita is a box operating between this line. Now, kita buat sedikit adjustment kepada operating line kita. Point 1 tadi dekat atas ini, point 2 sini. So, instead of doing that, we do a little bit tweaking. Kita start point 1 kita di sini, and then point 2 kita increase the temperature. Sorry, increase the pressure. So that it goes to a separate pressure line. It will follow, the process will follow a separate pressure line. Okay. So from point 1 to point 2 isentropic compression, kita compresskan water. After kita compress, there will be a slight temperature increment. That's why from here to here ada temperature T1, T2, T2 is higher than T2 is higher than T1. And then 2 to 3, from point 2 to point 3 kita buat constant pressure heat addition. That means this is a constant pressure line. Kita bagi heat in the boiler kan, kita bakar coal, or you can burn biomass or charcoal, or you can burn gas to give the heat, to provide the heat. So that you panaskan air dekat sini sampailah ke superheated point. Tadi dalam Carnot cycle kita berhenti kat sini. So untuk Rankine cycle, the heat addition until you reach a superheated point. Okay, and then from point 3 to point 4, expansion in the turbine. So dekat sini, masuk sini adalah superheated steam. So sini adiabatic expansion. Ni adiabatic is a straight line because this is entropy, temperature versus entropy. So straight line down. Instead of having to work with kat bawah sini, which is the liquid water mixture, now we are working with superheated steam, dry steam. So kalau you baca textbook ke, you baca text mana-mana sometime, superheated is also known as dry steam. Okay, dry steam ni is very important sebab you tak nak droplets lah. You don't want water droplets in the turbine because that water droplets can damage the turbine. Okay, so this is expansion sampai ke point 4 in a turbine. Now what comes out adalah mixture. You look at this point here, this is a mixture. Okay, so yang keluar dekat turbine ini adalah a mixture. And if you look at from this TS diagram, what is the quality of the mixtures ini? Is closer to saturated vapor line. So the X value ialah what is the X value? Agak je, angka je.
1. Close to 1.
Close to 1, yeah? So normally is about 90 to 100%. So that means 0.9 to 0.1 lah. Okay, maybe 95, 96 like that. That means kita ada keluar dekat sini ada very little water tapi a lot of steam. Kalau X di point 4 ini bersamaan dengan 0.9, maknanya 90% adalah vapor, 10% is liquid. Okay, So then kita condensekan everything, kita keluarkan Q. In the condenser, everything becomes liquid here. So for this to occur, you need to go sampailah you jumpa this compressed liquid line ataupun saturated liquid line. Okay, so sampai ke situ because tadi kita berhenti dekat tengah sini mixture. So we don't want a mixture because so that the pumping becomes easier, then we need to go down to the saturated liquid line. Okay, so once you have that, your cycle is complete. You selesaikan masalah dekat turbine, you selesaikan masalah temperature di sini because you can go higher temperature, superheated. Tak kira lah berapa temperature you nak pun, selagi the material can withstand, you can go. And you also solve the pump problem. Okay, so now ideal Rankine cycle replaces Carnot cycle. Okay, boleh faham? You follow me?
Faham, sir.
Okay, kalau tak faham tanyalah ya. Right, this is important. Kita tengok yang ni, then kita break for 10 minutes. Tapi before we break, let's go what the engineers have to do. Okay, you are here because as engineer, you kena analyze the energy. Okay, so from the basic energy balance, you have Q in, you have work component, you have heat component equals to change of the enthalpy. Okay, so this is already a simplified energy balance because dalam ni kita kata kinetic energy and potential energy are neglected and this is a steady flow process. So your energy balance is basically simplified to this. Kita cuma ada heat, kita ada work, and kita ada enthalpy. So if you look at here, heat yang masuk Q in dengan yang keluar QH, and then kita ada enthalpy di dalam kita punya working fluid. Satu lagi, work masa dekat pump, work dekat turbine. So that our equation becomes very simple. Yeah. Okay, the next thing to do is to further simplify. Dah mudah equation ni, so kita mudahkan lagi equation so that the engineer punya kerja becomes easy. So look at the pump. If you look at the pump, what are the components yang ada? Kita ada enthalpy yang masuk, enthalpy yang keluar, enthalpy in, enthalpy out, work in. No work out, no Q. So that our equation from here is now simplified to work pump in, ni work in sama dengan H2, H yang keluar, H exit minus H I, H inlet which is H1. So whenever you see pump, this is the equation that you use. Okay. So kalau kita nak kembangkan enthalpy is PV lah, yeah. U plus PV. So you boleh apa tu? Enthalpy equals to U plus PV. Okay. So kalau kita kembangkan this equation, enthalpy 2 adalah U2 plus P2V minus U1 P1V. Okay, so sini kita ada PV, P2V tolak P1V. Okay. U minus U cancel out. So you ada ini. Right, how about boiler? Now we go to boiler. So what do we see at the boiler? Kita ada enthalpy masuk, kita ada enthalpy exit, enthalpy inlet. We have Q in, we don't have work. So kita gantikan dalam equation 1 ini. Then kita akan dapati what we have is Q in, Q out tak ada, work in tak ada, work out pun tak ada, equals to H inlet, which is H3 minus H2. Okay, so it's just a matter of correlating heat and enthalpy. And if we go to turbine, so dekat turbine, what do we have? Work out ada sini, enthalpy 3 ada, enthalpy inlet, and enthalpy 4 is kita punya enthalpy outlet. Is there any Q? So Q equals to 0. Tak ada heat keluar dan masuk dekat turbine. So Q equals to 0. Sini tak ada. Kita ada work in. No, we don't have work in. Do we have work out? Yes, we have work out. Equals to H4 tolak H3. But because this is negative sign, kita rearrange. So kita dapat H3 minus H4. And seterusnya, if we go to condenser, bawah sini, so at the condenser kita ada Q out, work equals to 0, kita ada enthalpy 4 and then enthalpy 1 balik. So simplifykan kita punya equation untuk condenser, kita dapat Q out equals to H4 minus H1. So untuk rangkaian cycle analysis ini, selalunya soalan dia pendek, jalan kerja dia sedikit panjang, tetapi dia cukup senang, ya, because equation yang kita guna ini saja. But of course, again, untuk dapatkan nilai enthalpy kena relate balik dengan chapter-chapter yang sebelum ini. Remember kita ada Y sama dengan YF, Y average, YF tambah X, YFG, yang ada nilai quality. So these are the things that kita kena pakai. Right, from there kita boleh tengok thermal efficiency. Again, efficiency sama dengan the desired values over required values. So dalam case ini, what is our desired value? This work turbine out. What is the required input? The Q in. Okay. So kalau kita masukkan work net sini, because kita ada work in dan work out, so sini adalah net output, work net out over Q in. So you will get, this is desired adalah work yang mana? Work net, bukan work out saja, work net out over yang masuk ialah Q in. So this is it. And work net out, kalau kita tengok this here, yang masuk energy balance, work masuk dan yang keluar, so work net out equals to Q in tolak Q out. Okay, so it is equivalent to work out tolak work in. Okay, so once we have this, kita boleh gantikan sini. Ini kalau you gantikan this ke dalam work net in, so you akan dapat Q in tolak Q out over Q in sama dengan ini cancel out 1 tolak Q out over Q in. Yang inilah. Okay. So very simple analysis untuk sistem rangkai. Okay, so this is the final form yang kita nak pakai. But most cases ni equation untuk pump, untuk boiler, untuk turbine, untuk condenser. So the relevant relationship between heat, work and enthalpy. So kalau nak hafal, terpulanglah. Tapi saya tak mengajar student menghafal. Saya ajar, you just need to understand this diagram. And then you just hafal ini saja. Ya, 10.1 ni. So when you have pump, you apply the pump for the pump, then you akan dapat all these equation. So janganlah duk hafal-hafal lagi ya. Okay, so we take a break and then after break kita sambung balik. Let's take a 10-minute break. So kita continue pukul 1.20. Is that okay? Okay.
Yes.
Okay, now let's point number 3, step-by-step method saturation hydration, which is to calculate water saturation using the function. Okay, so we have covered this one. You basically estimate like this. Right? So basically, okay, the first is that whereby we have the dimensionless A. Okay, this is only the first dimension of B. Alright, we understood that. Okay, everybody get it? Right? So every time you have the calculated data on J function, and then after that what you got is like we so far I and we have this kind of method whereby we have a J relationship J and S. We have J equals to A constant as well as 1. So it is in the boundary relationship. Okay. So the A and B is what? Right? So this A and B we are going to apply when we want to calculate our distribution using this K function. We are going to apply that for the multiplier. Okay? Understand? Everybody get it? Okay. Now this is how it the plot K function distribution will look like. Okay. Every time we create like this, so hopefully get any that doesn't look like this one. So most of all the time we will have this kind of relationship. Okay. So we are going to have our determine our A and B. Okay. This is if we are using next slide, because we can put the trend line there. But if we don't have the we are using manual calculation. What okay? Can you tell how are you going to derive for example? How can we do that? Any solution? If we don't using we are using ESL. Yeah, we do the right? Okay. We want to find it. We have straight line, right? I visit the video. Make sure that check try to play around with it because I'm telling you they are this is like very nice straight line. There are going to be some like so we have to adjust this and another one is so not we look at the improvement method because that because students probably are fine and this because I think
Okey, kita sambung. Right, the first example. Consider a steam power plant operating on the simple ideal Rankine cycle. This is example 10.1 dalam textbook you all ada. Steam enters the turbine at 3 megapascal and 350 degrees Celsius, condense in the condenser at a pressure of 75 kilopascal, determine the thermal efficiency of the cycle. So again, when you kalau you ada this type of question, you transfer the informations into the diagram. Memadai buat kotak-kotak pun cukup. Right, so you masukkan 3 megapascal here, 350 degrees Celsius, and then at the condenser we have 1 point here, determine thermal efficiency. So cuma diberi 3 information sahaja, but we know that this is constant pressure. Okay, so from this line here, this is a constant pressure line from point 2 to point 3. So from point 2 to point 3, this is also 3 megapascal. And we know that dekat condenser ini, at the bottom here, is a constant pressure line juga. So kalau sini 75, over here at point 1 is also 75 kilopascal. Okay, so daripada just 3 information, now we have more information on our diagram, and we know also that here S3 and S4 equals, yeah, S3 equals, because this is adiabatic expansion entropy ataupun isentropic process, so entropy change is 0, so S3 equals to S4. Similarly untuk point 1 ke point 2, so S1 sama dengan S2. Okay, so now we have more information to solve the problem. Soalan tanya thermal efficiency. Okay, I think saya berhenti sekejap, azan dekat rumah saya ni. Okay, so we continue. Thermal efficiency, work net over Q in, desired over required. Then you can arrange the equation menggunakan these two correlations. So 1 minus Q out over Q in. Okay, so the question here ialah, for us to calculate this, we need this value Q out, we need Q in, or we need work net, which is Q in minus Q out, work turbine out minus work pump in. So in other words, for us to be able to solve this, kita perlukan nilai-nilai 1, 2, ataupun kita perlukan dua nilai ini. So you boleh calculate, you boleh tentukan, okay, menggunakan energy balance yang kita dah tengok tadi. So the solution is this, right? So we will need to be using table A4, 5 and 6 for this problem. Tengok as step 1, 75 kilopascal saturated liquid. So macam mana kita tahu? Because here is saturated liquid point. So dapatkan nilai enthalpy. Enthalpy at point 1 is equivalent to HF at 75 kilopascal. So tengok table pressure table. So table A5. So you will have 384.44 kilojoule per kilogram, and V1 at this point here is also VF because dia duduk atas saturated line ini. So VF 0.00137 meter cube per kilogram. Okay, so selesai. Because remember, untuk case ini kita perlukan H1, kita perlukan H2, H3, H4. Okay, H1. The next one is step 2, P2 sama dengan 3 megapascal, because this happen at constant pressure line. Kadang-kadang diberi pressure di sini, then you know lah the other side is also 3 megapascal. Isentropic process, S2 minus S1. So work pump is isentropic, ya. Sini isentropic from point 1 to point 2 isentropic. So S1 equals to S2. Here S1 S2. So work pump in, equation untuk pump is H2 minus H1. So VP2 minus VP1. Okay. So dalam kes ini dia nak cari work. Macam saya kata tadi, you can calculate semua sekali and determine you nak pakai yang mana, ataupun you boleh fokus kepada Q contohnya. Okay. But for this question, ditunjukkan solution di sini, you dapatkan pump in for work. V1 ada from state 1, P2 ada because 3 megapascal minus P1 which is 75 kilopascal is given dalam soalan itu 75 kilopascal. So you should be able to solve this, dapatkan 3.03 kilojoule. Okay, and once you ada enthalpy, work, so kita boleh buat energy balance di sini. Enthalpy ada, so we know enthalpy 1, we know work pump 1, and we wanted to find H2. So energy balance dekat situ, yang masuk H1 plus work in equals to H2. Okay, so if you want to find H2, just tambah H1 plus work in. Okay, so H2 equals to H1 plus work in, you dapat 387.47 kilojoule. And then move on to state yang ketiga, this is at the boiler. So P3 is given 3 megapascal, temperature is given, you have temperature, you have pressure. So you boleh tentukan nilai enthalpy which is H3. So nak tengok table mana ya? Table pressure ke table temperature? If you are given temperature, you are given pressure, you have two independent properties. So which table are you going to check here? Is it table A4 or table A5? Or table A6? Okay, sini dah simplify. You know the pressure 3 megapascal, temperature 350. Rule yang pertama, kalau kita nak tentukan enthalpy, enthalpy is a function of T. So is a function of temperature, so always refer temperature table. Ya, jangan tengok sama juga dengan internal energy which is CV. So both enthalpy and internal energy, they are a function of temperature. So tengok table A4 lah ya. Jangan tengok table pressure table. Okay, but in this case slightly different sebab first you need to determine at 3 megapascal, 350. So your working fluid, the water, is it saturated vapor, a mixture, or superheated? So you need to go to table A4, check 350 degree Celsius, compare dengan pressure. So kalau you go to table A4, ulang balik ya yang kita dah pelajari selama ni. So you have 350, you ada dekat table A4 350 degree Celsius, you ada P saturated. So you tengok P saturated di situ, and you compare dengan P given. Okay. So kalau P V, if this P is lower than P set, then you have superheated. So kalau superheated, you kena tengok table A6. So kalau saya tengok roughly macam ni, saya pun tak check, but I think this is going to be superheated lah, 3 megapascal at 350. So most probably you kena pergi tengok table A6. Okay. And from table A6, you should be able to check at this temperature and pressure, enthalpy 33116.1, entropy 6.7450. So kita dah ada untuk point 3, enthalpy ada, dan S3 pun ada. So the moment you ada S3, you also have S4. Okay. So at point 4 kita ada S4 and P4. We know that that point is a mixture. Okay, this is ideal Rankine cycle. So kat sini adalah mixture ni, bukan vapor. So this is a mixture. So kalau mixture, kita kena guna equation yang ada X tu. Here we have two independent properties. Pressure is given, entropy is given, ataupun entropy is available. Then we use this equation, yeah. S4 equals to SF plus SFG multiplied dengan X. So rearrange the equation, you dapat X4. Once dapat X4, 0.8, gantikan dalam equation yang sama untuk dapatkan enthalpy. So HF plus X4 HFG. And tengok daripada table nilai HF dan HFG at P4 and S4 values. So you should be able to calculate the enthalpy 4. Okay. So now kita dah ada semua values. Then kita boleh buat, kalau kita nak guna this equation, gunakan energy balance untuk dapatkan Q in dan Q out, ataupun kita boleh guna work equation. Right, so let's see kalau kita nak pakai Q in and Q out untuk tentukan efficiency. Q in sama dengan H3 minus H2. Go back to this boiler. So energy balance di sini, yang masuk Q in, what else yang masuk? Enthalpy 2 tambah H2 sama dengan yang keluar enthalpy 3. So Q in equals to H3 minus H2. So H3 minus H2, you can get the values. Similarly untuk Q out yang dekat bawah tu, you rearrange the equation so that you can get H4 minus H1 and then you get the value. So once you ada Q in and Q out, gunakan this equation, so you will get 26%. You see, this is 26% efficiency untuk ideal Rankine cycle. Okay, very low, yeah. Right. Kalau kita nak guna Q in dan Q out, you can also guna work turbine out. So energy balance dekat turbine. Go to this turbine. Energy balance yang masuk enthalpy 3. Anything else yang masuk? Tak ada. Yang keluar sama dengan work turbine out plus H4. So therefore work turbine out equals to H3 minus H4. So H3 minus H4 dapatkan the value because kita dah tentukan dekat sini yang tadi all the required values, and then from work net equation, which is work turbine out minus work pump in, work net, work net ni, work net ni maknanya yang untuk the whole thing sini, kalau kita ambil the whole thing, yang masuk is work in dekat pump, yang keluar work out turbine. So work net di tengah-tengah ni, yang masuk tolak yang keluar lah kan, ataupun yang keluar tolak yang masuk. Okay. Kenapa work net di sini yang keluar tolak yang masuk, bukan yang masuk tolak yang keluar? Anyone? Okay. Because work net sini adalah work net out. Okay. So because work net out, so mestilah work turbine out minus work farm in. Because kita nak, this is energy generation, so kita nak work net out, bukan nak work net in. Right, so if we use this equation, all the values work turbine out, work pump ni kita dah tentukan. Sini ada work pump in, and then work turbine out ni kita tentukan tadi, so just masukkan dalam equation lah. Right, seterusnya, or we can also use this equation, work net over Q in. So kita dah ada Q in tadi, dan kita calculate work net, gantikan, you will always get the same value of 20%. Right, so this question is about ideal Rankine cycle. So soalan yang kedua yang boleh tanya ialah what happens to actual plant efficiency, because this is ideal. We know that in this world tak ada yang practicalnya ideal. Okay, so for ideal plant, of course lah, efficiency will be lower sebab irreversibilities. And how about Carnot power plant? Carnot mestilah the maximum output, the maximum efficiency, so we can use temperature difference to calculate the efficiency. Now it is at 0.4 ataupun 41.5%, much higher than 26%. Okay, because kenapa? Sebab Carnot is reversible heat engines. So you know Carnot reversible maximum efficiency, ideal lower, which is 26. Kalau the actual plant yang kita operate dekat kapal, dekat Port Dickson, dekat Parker, dekat mana-mana tu, will be lower than this value. Okay, because dalam plant yang ada hari ini is full of irreversibilities, friction dan sebagainya. Okay, boleh faham? Jelas?
Jelas.
Okay. Now problem 10.22 dalam soalan textbook 10.22, the unit is given in, sini saya dah tukar jadi matrix SI, tapi dalam textbook the question is, sorry, rasanya tak silap saya soalan dalam textbook guna imperial PSI units instead of MPA. Okay, yang kedua ni I think kita nak kejar masa, I need to finish up. solution is given dalam slide, dalam text notes tu. So please go through. We use the same principle, the same concept, the same equation. Okay. The only thing yang you all nak kena aware ialah di sini. Ni ramai yang selalu confuse ni nak guna ni at this point. This is mixture. Majority selalu tak ingat point 4 ni. Okay, so you need to use X equation. Right. Now, how can we increase efficiency of the Rankine cycle? Macam kita tengok tadi, there's too much difference between Carnot and ideal Rankine cycle. So now scientists, engineers, technologists are looking at ways how to improve efficiency. Now there are 3 ways. Senang saja. Again, you boleh hafal. Kalau tak nak hafal, then tengok dekat this diagram. Okay. Pertama sekali, remember how can we increase the efficiency? Efficiency is given by the area dekat dalam ni. Okay. So kalau you nak area di dalam sini besar, the first thing you can do ialah you reducekan condenser pressure. That means instead of operating at this pressure, you operate at 4 prime punya pressure, because this is lower pressure than P4. This is P4 line, this is say P4A lah katalah, ya. So this is higher pressure, this is lower pressure, this is lower pressure. If you operate lower pressure, what happen? You have extra area di sini. So yang asal ini, now you have extra. So this is extra efficiency. Okay, itu yang pertama. You operate at lower pressure. Yang kedua, instead of you stop dekat sini, dekat boiler ni, you heat, you stop dekat sini, you keep on heating. Okay, to high temperature. This is temperature kan? This is T saturated. If you stop here, then you will have bigger area. So initially, this is your area. Because now you increase the temperature, then you have other additional area here. So additional area means higher efficiency. Okay, so yang kedua, kita superheat the steam to high temperatures. Kita improve the temperature daripada boiler. Ini steam yang keluar daripada boiler. Right, yang ketiga, tadi kita work on the temperature. Next, we work on the pressure at the boiler. So remember that this line adalah constant pressure line. So if we work at higher pressure for the boiler, boiler is 0.2 to 0.3, yeah? So you follow a different line. Okay. So now, if you follow a different line, the same temperature maximum, what happen is you ada this extra area dekat sini. Okay, you remove this, tetapi the overall net efficiency will still be higher than what you get from here. Okay, so there are 3 ways of increasing the efficiency for Rankine cycle. Pertama, saya ulang, work at lower condenser pressure, 0.4 to 0.1 is condenser. Second, dekat boiler kita guna higher temperature. And then third, again dekat boiler, use higher pressure. So all this will increase the efficiency. Sekarang pukul lagi 5 more minutes. I skip this example because this example ada dekat page 578. please go through this example so that you know what to do. Tetapi the conclusion of the example ialah, if you work at this condition, thermal efficiency for ideal Rankine cycle, yang ini, yang asal ni, A ni, so this is ideal condition, okay, ideal Rankine cycle. Your area is like this. This is your efficiency. Okay? Values you have to calculate lah. Okay? But what I'm trying to show here is that from this diagram, you can see which one will give you the lowest and highest efficiency. Okay, so this is thermal efficiency for ideal Rankine cycle. If you do the exercise, you will get this line, and this is the area that will give you the efficiency. Now, if the steam is superheated, that means instead of 350, push up to 600 to here, 600. So you have extra area under the graph. This means higher efficiency. Next, if you further increase the boiler pressure and at 600, that means 3 megapascal is this line. So if you now operate 3 megapascal tadi kat sini. Now if you operate at higher pressure, 15 megapascal, and you maintain the 600, so you will have the extra area under the graph here. So these are also higher efficiency. So in A is the lowest. Okay, ini mid, ini highest. Yeah, if you calculate the efficiency lah, so maybe this value is, let's say, 40%. This one could be 35%, and this one maybe 25%. Okay. Reheat. Now again, technologies tak puas hati, they still wanted to improve the efficiency because efficiency equals to money. Okay, so power plants, they want to make money, so they want to improve efficiency. Then there's one more ways to improve efficiency, by reheat. So what happens is, we follow the same Rankine cycle, and then the steam kita masuk dalam turbine. This is the turbine. Yeah. Keluar turbine dah spend, tapi masih lagi in superheated ataupun in vapor state, and then kita reheat dalam boiler. This is boiler. Reheat ke higher temperature, and then turbine again. So dalam gambarnya macam ni. Come up from the boiler, the high pressure steam. This is high pressure steam, high temperature steam. So high temperature, high pressure steam go to high pressure turbine. Keluar daripada turbine, dia dah lower temperature, lower pressure. Kita supply masuk dalam boiler, panaskan semula, and this time to the same temperature, because boiler operates at the same temperature. So you go back to the same temperature. Sini temperature is the same, 3 dengan 5 ni. And then supply ke low pressure turbine. So ada dua turbine connected, high pressure and low pressure. Okay, so this is a turbine, and then come out daripada sini, then it goes to typical point, which is the mixture. So if we do this, you see the extra area that you can get for this cycle. Okay, and the equations terlibat yang inilah, so you can have a look. That's why dalam banyak case kalau you buat banyak cycle reheat, keluar turbine, panaskan dekat boiler, masuk balik turbine, keluar turbine nombor 2, panaskan balik, keluar turbine nombor 3, panaskan balik, you do many times, then you keep increasing the area, then that means you keep increasing the efficiency. Okay, so yang inilah yang ada low pressure dengan high pressure, and then ada satu lagi dekat sini, low pressure turbine. So you ada 3 turbine ni, ya. First high pressure, keluar panaskan economizer ni, and then masuk balik pergi ke low pressure turbine, kemudian pergi ke another low pressure turbine. Okay. So dalam case ini, inilah dia punya bentuk dalam. Kalau you take out the turbine punya casing tu, these are the blades in the turbine. High pressure, this is medium pressure, and then low pressure. Okay, so ataupun intermediate lah tadi, medium pressure. Example 10.4, page 557, you can have a look. I think that's it for today.